Today I get the honor to introduce one of my colleagues. The gentleman's name is Ray Denkewicz, who joined Hayward in 2008 with the responsibility of overseeing global sanitization, chemical automation, including salt chlorination. He's considered a leader in developing new and emerging global technologies and opportunities for business. Ray is the former CEO of Vortex Corporation in Prescott, Arizona. Prior to that, he was the vice president of Triton Systems in Chelmsford, Massachusetts. Additionally, he was the senior vice president, general manager of Evionics Incorporated in Hawthorne, New York, global product and technology manager for PQ Corporation in Berwyn, Pennsylvania. So Ray has definitely been in the industry for quite some time. Ray's pool experience dates back to 1994, where he worked for Zodiac Pool Care as the vice president of technology, developing a natural mineral purifier line for pools and spas. Ray was also the co-organizer, co-editor of 3 symposiums in pool and spa water chemistry published by NSPI. Ray has more than 100 U.S. and foreign patents, has been published in more than 20 scientific publications, holds various degrees, including a master's and BS in chemical engineering from Worcester Polytechnic Institute. Also has PhD studies in chemical engineering and materials science and engineering from University of Pennsylvania and Pennsylvania State University. So he made me read all of that, by the way. I was going to do something all sentimental, and he's like, no, don't do that. I need to gain credibility. And I said, yeah, you're right, we're Hayward. So now introducing my friend, my mentor and colleague, Ray Denkewicz.
Thank you. Thank you, pal. Thank you. Good morning, everyone. I'm a newbie to this conference, and I got to say I'm very impressed with the way this has been organized and thought through. And so I'd like everyone to give a big hand to all the organizers, NSPF, Lindsay and Michelle, Tom. Great job. I'm honored to be here. I would be remiss if I didn't acknowledge my co-authors. Dr. Jim Bolton, you may recognize as being a leader in the UV space. He was the former executive director of the International UV Association, former editor of the International UV Association News magazine. He has about 250 publications, and a few weeks ago, he was given the Lifetime Achievement Award by the International UV Association. I consider him a friend and happy that he was part of this investigation. Dr. Kelly Bright, she's a senior research staff member at the University of Arizona. She's been there for about 20 years. She got her PhD there under Dr. Gerba. She's an expert in disinfection chemistry. Professor Gerba is also a co-author here. Maybe you all recognize his name. He's a world leader in the disinfection of primarily drinking water, has over 500 publications. You see him oftentimes early in the morning on CNN or Good Morning America talking about disinfection of something, whether it be toilet seats or cart handles in grocery stores. And he's been on the technical advisory board of the EPA for a number of years. And also a colleague of mine at Hayward, Don Boyd, at the time of this work was a research engineer. Tom asked me to consider why we're really here, and I would say this slide sums up for me why I'm here, and that is the fact that most people utilize the swimming pool, whether they realize it or not, effectively as a restroom, okay? And as you know, that to do so can be accidental. In the case of fecal coliform, turns out that Chuck Gerba in 2000 determined that every bather releases about 0.14 grams of fecal matter into the pool. Now, if you ever meet him, ask him how he knew this. But I can tell you it involved 18 of his female graduate students where he would buy their underwear every day for $5. And that's a fact. And he said, you don't really want to know the lady who had the 10 grams. Also in that study, they determined the number of protozoan and enteric viruses that existed in those that were sick. So that number there is on the order of 10 to the 5 to 10 to the 10th. Colony-forming units or plaque-forming units per gram. Elmer et al. In 2007 determined that skin cells contribute to accidental release to the tune of about 6 million coliforming units per bather in a 15-minute period. Gunkel and Jessen in 1988 said that urine is involuntarily released at the rate of about 30 milliliters per bather. Now, I just went to Professor Blatchley's presentation, and he has some data that's, 15 minutes old now, and I'm happy to say that his data is right in line with that, probably a little bit higher. He was looking at urea in swimming pools and asking the question, if that urea is attributed to the urine, how much urine would the bathers have released? Urea, by the way, is a major component in urine, as it is in sweat. Judd and Bullock in 2003 concluded about 200 milliliters per bather for a typical bather activity. I think the number that I'm used to is a liter per hour of sweat. And then, of course, you have all your consumer products, cosmetics, suntan lotions, and things. This is the accidental release that gets into the pool. You also have the intentional release. Okay, so I had breakfast with Debbie Phelps, and I don't know what possessed me to mention this to her, but I did bring this up to her about her son urinating in the pool, and I told her we were here to take care of all the associated problems with that. So really, that's kind of the why we're here, is because we have challenges with the swimming pools in terms of disinfection, and I want to talk to you about a technology that has really been around for decades. It involves just UV and ozone, but putting them together in a unique way to accomplish some really fabulous things, as you'll see. I won't spend a lot of time on recreational water outbreaks. You've already seen those talks. Doug did a good job standing in for Michelle Kavanaugh, and Dr. Beach presented their information. And this is the list of the most common causal agents in recreational waterborne illness. And you'll note that two of them on this list, cryptosporidium and adenovirus, are not well addressed by chlorine at typical swimming pool water levels. So those two organisms are going to continue to survive for the most part in a typical swimming pool, and so we need to do something about that. And of course, all of these recreational waterborne outbreaks can lead to some serious consequences for individuals, whether they be immunocompromised or not. So it's a serious problem. It's not just finding organisms in the pool. It's really about the true health and well-being of real people. And you heard Tom Lachaki this morning talk about the fact that we're all together as one family. And so we really have to do something about this to help our fellow swimmers. Cryptosporidium, of course, has been associated with the primary causal agent. And as you know, chlorine does very little against that. UV has been the primary breadwinner, at least from the standpoint of drinking water. That's how UV became so popular in the drinking water circles, when in the early 1990s in Milwaukee, there was a cryptosporidium outbreak. Nearly 100 people died as a result of that. And that's when the drinking water industry started embracing UV as a secondary disinfectant. I won't go into this. You've heard about the Atlanta studies and just the detection of various organisms in those waters. So how do we deal with the problem? Well, chlorine is an excellent disinfectant, and I'm happy that chlorine was discovered and invented and has been used for, better part of a century to disinfect water. And so it does a great job, but it's not the end-all being for a disinfectant, only because there are organisms out there that have figured out how to invent themselves around chlorine as a disinfectant. Cryptosporidium, adenovirus, and Naegleria fowleri. And if you don't know what that is, you should read up on it. That's that brain-eating amoeba that it's rare to get infected, but if you do, you have a 98% chance of dying. And as Professor Gerber likes to say, if you're the 2% that lives, chances are your IQ is in the single digits. UV light is an excellent disinfectant, and it's a great supplement to chlorine, but it too isn't perfect, all right? In that there are UV-resistant organisms. Adenovirus is one, and Naegleria fowleri is another. And Naegleria fowleri is very rare to find in swimming pools, mostly found in natural lakes. But it's something that we have to pay attention to. I don't think people were looking for it in the past. And so it's a real issue. Ozone, another excellent supplement to chlorine. Perhaps this is why the CDC is recommending either UV or ozone as a supplement to chlorine as part of the Model Aquatic Health Code. But it has some challenges depending on how it's generated. It could be expensive in terms of capital cost. As you know, it has a short half-life, maybe about 18 minutes in water. And you have an off-gassing issue if you're generating a lot of ozone with corona discharge. And it is ineffective, according to the studies we've done, against Naegleria. So right now, we haven't found anything that addresses Naegleria properly. You know all this that I'm telling you because you can look all this information up in the literature. So in terms of chlorine, you can look up these CT tables, concentration times time, and it tells you how effective chlorine would be against these different organisms. And I just showed you a sampling up here, wanting to leave you with the impression that chlorine does a great job against some organisms, but it's difficult to address other organisms. Okay? Also, we know that chlorine has the side effect of generating disinfection byproducts, some of which can lead to eye irritation and respiratory irritation, particularly in closed spaces. Okay? And also the chlorine, free chlorine has to be stabilized to the effects of sunlight. UV light, we talk about UV light in terms of dose tables. So just like chlorine, instead of concentration times time, we're talking about intensity times time. So that's an IT table. So this gives you an idea of how much UV dose you would need to address the organisms listed here to accomplish the 3-4 log reduction that I show. And you can see here that adenovirus is very challenging. When the EPA started to require that municipalities treat groundwater, in the past it wasn't a requirement that municipalities had to treat groundwater with chlorination. When they did so because they discovered that adenoviruses exist in groundwater, less common in surface waters. And UV, which had been very effective in dealing with the cryptosporidium issue, was not effective in addressing adenovirus. And so you'll see the EPA has raised their recommendation for the UV dose in drinking water plants from like 40 millijoules per square centimeter up to like 186 to achieve the same effectivity. And it was all driven by the adenovirus. Ozone is very effective across a wide range of organisms. It oxidizes the bejesus out of just about everything. So it's a great disinfectant. But it didn't do much in terms of taking care of Naegleria fowleri. I don't know why. Haven't had enough time studying it yet. But it's an extremely powerful oxidizer. It's excellent at killing all kinds of microorganisms. It doesn't have a residual, as you know, and it's ineffective at inactivating that nasty organism called Naegleria. So the drivers for supplementary technology use, I hope are obvious, that there's no one disinfectant that does it all. And so the CDC, through the Model Aquatic Health Code, is really encouraging the use of a supplementary disinfectant for high-risk venues, aquatic venues. In 2010, last time I looked, there were 8 states that mandated the use of supplementary treatment. And in their Designing and Operating Public Swimming Pool Facilities Guideline, the CDC has been recommending for a number of years the installation of a supplementary disinfection system such as UV and ozone. So they're being very consistent in what they're recommending over the last several years. High-risk venues, to me, mean children and high bather load. So I was able to find a representation of what that means. Okay? I mean, this, to me, is children with high bather load, okay? And I don't know what possessed me to do this, but I looked at that picture and I said, I wonder what that person grew up to be and what that person grew up to look like. So I used computer animation, which I'm not very good at, and I simulated what this person looked like as an adult. It turns out it was Tom Lachocki. And, now my computer animation may be flawed, but I'll leave that up for you to decide. But, you know, he had to get his love for aquatics somewhere. And this is just one theory, okay? This will probably be the last year I'll be invited back. So it's been good being with you. Let's talk a little bit about the mechanisms of inactivation, because I think that's important, because there's a story here. With respect to viruses, ozone, being the great oxidizer, directly oxidizes the receptive and recognition proteins that the viruses use to bind to the host cells. It also rapidly degrades the membrane envelope such that the capsid is destroyed, the RNA is released, and the RNA itself is oxidized. So it really obliterates the whole thing. And this is work that you can find in the scientific literature dating back to as early as 1980. UV light, on the other hand, operates by a different mechanism. It inhibits genome injection by destroying the protein coat and the membrane envelope. But it also inhibits genome replication by messing with the RNA. Okay, it literally transforms the RNA into other compounds such as uracil dimers and hydrates, or it cross-links it to other molecules in such a manner that the products that are generated, the host virus cannot repair. Okay? Chlorine, on the other hand, acts similarly to ozone in the fact that it acts like an oxidizer, degrading the protein of the membrane envelope and the capsid, and destroys the permeability of that unit and ultimately deteriorates the RNA. And this is work that was published, by the way, as recently as a year ago by a group, Wigington and Known, I think out of the UK. With respect to bacteria, ozone, again, being the great oxidizer, oxidizes the cell wall. Things start to leak out. It oxidizes the phospholipids and lipoproteins. Chlorine acts in a similar manner, but depending on the study, they see slightly different mechanisms of action. It also depends on the bacteria at play. UV light, being different again, induces the formation of lesions and pyrimidine dimers, and it blocks DNA replication and RNA transcription. It also does some oxidative damage to the lipids and proteins, disrupting biological function of the bacteria. So there was an interesting case study, very simple, straightforward case study on cryptosporidium with ozone. This was as recent as 2010, where this group looked at cryptosporidium in the presence of ozone at a dose of 3 ppm, and they could detect readily the massive degradation of the individual oocysts and leading to complete inactivation. You know, so the reason I showed you that is because I wanted you to contemplate the fact that these different disinfectants operate differently. They all bring to the table something unique. And so it occurred to me, like, well, why not have them all, right? If you can afford it, why not hit the pool water with every single possible thing you have in your arsenal to address these nasty issues? So I want to talk to you a little bit about having the best of both worlds, both UV and ozone, along with chlorine. And what inspired me was back in 2007, there was actually 2006, a group out of Mississippi State. That should be 2006. It says 2007 at the top. I apologize. A group under the leadership of Mag Banua did a very interesting study on the synergy of UV and ozone against E. coli. And what they did is they looked at E. coli with UV alone, they looked at it with ozone alone, and they looked at the impact of using both disinfectants. And there's lots of data in that paper, but I'll show you one table that I pulled out that kind of tells the story, the entire story of this paper. In this case, they were able to get a 3-log reduction of E. coli with 1.58 millijoules per square centimeter of UV dose if UV was the only thing they used. And with ozone, they were able to accomplish that same log reduction with a ozone dose of 4.43. But what they discovered when they started putting them together in combinations, that they were able to reduce the UV dose by a factor of 18 and the ozone dose by a factor of 4 and still accomplish the same thing. Okay? And I attribute that to the different ways these things act on an organism, so they actually are synergistic, in my view. Now, that's a lot of techno-speak I gave you on the last couple of slides, so let me put it in the vernacular of Batman. This is what Batman might say about UV and ozone. Boom, pow, kaplooey, whatever, all right? Let's talk about what's really going on. In the scientific literature, so this is not something Hayward invented, but the scientific literature talks about the fact that when UV and ozone interact, what's probably happening is you're producing hydroxyl free radicals. And the mechanism is as simple as ozone is degraded in the presence of the UV light to form a hydrogen peroxide intermediate, which reacts with oxygen to ultimately form 2 units of hydroxyl radicals. So for every ozone molecule that's destroyed by the UV light, you end up with 2 units of hydroxyl-free radicals. Okay? Now, hydroxyl-free radicals, you've probably heard about these. They're very potent oxidizers. The second most potent oxidizer known to man, next to fluorine. And fluorine isn't something we're about to use in swimming pools because we'll start dissolving people. But it's a very strong oxidizer, more so than ozone and chlorine. In fact, studies that have been done on using hydroxyl radicals to destroy organic compounds, and you can see the list here ranges from olefins to alkanes to alcohols, ketones, aromatics. Virtually every kind of backbone you could imagine for an organic compound is represented here. And the hydroxyl radical was orders of magnitude faster in its action and reaction with these compounds than ozone was. And we all know ozone's a great oxidizer, but hydroxyl radicals are even more so. So let's talk about how we're going to make a practical system out of a UV ozone system without breaking the bank. Let's start with a basic vessel, okay? So we have a hypothetical vessel here. It's got a water inlet and a water outlet. Let's imagine we put inside that vessel a UV lamp. You with me so far? All right? This is common. It's being done today. People put UV lamps in vessels all day long. They call them UV reactors. Those lamps are always surrounded by a sleeve, typically quartz, to protect the lamp from the water phase. So I'm representing that gray area is the sleeve around the lamp, and you naturally create an air gap in that sleeve. Now, if you buy the right lamp, these lamps will produce 2 different wavelengths. These are low-pressure UV lamps. The 185 nanometer light and the 254 nanometer light. Now, if you know about UV disinfection, you're very familiar with 254 nanometer light as being the active component in the disinfection of microorganisms. But the 185 nanometer light, coincidentally, is the perfect wavelength to make ozone. And so all those UV-generated ozonators out there take advantage of the 185 nanometer light to make ozone. So in this scenario, if I were to build that vessel, I would be making ozone in the air gap, and I would be irradiating the water with UV 254. UV 185 does not penetrate the water phase. It actually is captured right there at the surface of the quartz sleeve, at the water quartz sleeve interface. So now imagine that if I'm making ozone in that air gap, why don't I just take it out and inject it into the water? And by putting it in the water in front of the vessel, I can now create a UV plus ozone system without having a whole separate ozone generator. Now, if you've been by our table this week, you've already seen we have a demo, technology demo of exactly this. Okay? Here's a prototype we built, and this one was for flow rates of about 10 to 30 gallons per minute. We put it on our pool at our factory up in Rhode Island, which happens to be a 28,000-gallon pool. That one's a salt chlorinated pool that's ORP controlled. And that's important because I want you to know that we knew exactly how long the chlorinator ran every single day, and we knew exactly how much chlorine was being delivered to the water. And over a 41-day period, a random 41-day period, we determined that we were using 0.62 pounds of chlorine per day with no ozone or no UV. This was just using salt chlorination based on environmental factors and bather load. So then we employed the UV ozone prototype you just saw, and over a subsequent 26-day period, we saw a reduction down to 0.292 pounds per day, which is a reduction of about 53% chlorine use. Now, I understand I cannot do the perfect control experiment. These, by very nature, the 41 days was done in sequence, and then I started the UV ozone system immediately following for the next 26 days. So you don't have a perfect control, but this is some indication that the UV ozone's picking up some of the work, doing some of the heavy lifting, and helping chlorine beat back on the demand. We looked at combined chlorines in the same pool. Again, without UV or ozone, during a 17-day period, we had a combined chlorine level of about 0.4 ppm on average. It varied. And then we activated the UV ozone system as part of the overall water treatment process, and we saw a 54% reduction during the following 17-day period. We've done this on smaller bodies of water, a smaller system with a 250-gallon tank. In the absence of, with UV only, we didn't see any reduction in chloramines. Now, this is low-pressure UV. With medium-pressure UV, you might get some benefit. But over a very short period of time, we had very high turnover, probably circulating the 250 gallons at maybe 5 gallons a minute. So we had very fast turnover of this water. And then when you activate the UV ozone device, you start to see an immediate impact on the combined chloramines. And then I actually went home to sleep, and when I came back in, it was down to 0 in the next morning. So you can see the impact on this small scale as well. We did another interesting study on urea, again with a small device. We were using the very vessel that's out on our table. It's about 2.3 liters. We had it hooked up to literally a 5-gallon bucket of water. We inoculated it with 23 parts per million urea. We used urea because we knew urea was a primary component in urine, and we know it's a major component in sweat. I think it's the second leading contributor in terms of chemistry to what's in sweat. This device puts out about 40 millijoules per square centimeter UV dose. You can run it with UV only, you can run it with ozone only, or you can do it with a combination. We also compared it to chlorine, and this shows you the data. Chlorine doesn't touch urea. In fact, Professor Blatchley confirmed that 20 minutes ago in his talk. UV only didn't do anything. Ozone did a nice job of degrading it, and the UV ozone was much faster. In fact, we plotted this as a second-order reaction and determined, based on the rate constants, that the UV ozone system was about 3 times faster than ozone alone at reducing the urea. We've also done a large number of studies under a contract to Homeland Security, which I didn't get permission to disclose those results to you, but I will tell you, and I hope you would believe this, that we looked at the University of Arizona's Water Quality Center under the direction of Professor Gerba. We looked at feline calicivirus, MS2, E. coli, adenovirus 2, and Naegleria fowleri, and in all cases, we saw a synergistic effect when we combined the UV and ozone together as opposed to UV or ozone alone. In fact, we haven't found an organism that the combination does not address. We didn't invent this. UV and ozone together have been known for decades. Here's some studies. I mentioned already the Magnet-Benua study. There was another one in 2001 on disinfection byproducts, another one in 2005 on trihalomethanes and haloacetic acids, and in all cases, they were seeing tremendous reductions in those compounds. Some other studies on geosmin and methyl isoborneol and bromate. A study on poultry water. They were actually looking at E. coli there. And some others in the drinking water area on estrogen-based compounds and other micropollutants from pharmaceuticals. So I would submit to you that overall UV and ozone is effective at reducing chlorine demand because it's doing some of the heavy lifting. It reduces chloramine levels, which has potential implications for air quality. I think you all know that, or it's obvious that that would be logical. It oxidizes urea. And it's great at inactivating all kinds of microorganisms. I believe the source of its efficacy is the combination of the 3 disinfectants, a trifecta, if you will, of disinfectants. A question I often get asked is such a system affordable? Well, I'll let you decide. I've put up a hypothetical scenario here. Let me walk you through it. Let's imagine that we have a 100,000-gallon commercial pool, and these are my numbers, so you can plug in whatever numbers make you comfortable. If that pool were operated on sodium hypochlorite, I submit to you that that pool would use about 2,700 gallons of liquid chlorine annually. And let's assume, for this discussion, that that chlorine costs $2.25 a gallon, fully loaded, in terms of getting that chlorine to the site, transportation, etc. That's $6,000 in chlorine a year. That same pool, if operated on calcium hypochlorite, because it has a lower free chlorine, available chlorine level, you're going to need 4,000 pounds of cal hypo. And let's assume it's also available at $2.25 a pound. That's $9,000 for that pool. Now, let's assume that there were available a UV ozone system that could satisfy some of the demand on that pool, and that system costs $6,000, let's just say. Well, if you're a finance person, you're saying to yourself, I need to return, my return on my investment has to be less than 3 years. Meaning that $6,000 investment has to pay itself back within a 3-year period, or $2,000 a year for 3 years. So I did some math, show you what it looks like. In terms of calcium hypochlorite, if you were able to get a 22% reduction in the chlorine use on that pool, that type of system would pay itself back in a 3-year period. Liquid chlorine was a little bit more affordable in my example, and you would need a 33% reduction. Okay? And I put the 3-year return on investment line at $2,000 because I told you you need to pay yourself back $2,000 a year for 3 years to get a 3-year ROI. Okay, so is it feasible to get 22 or 33% chlorine reduction? Well, I have a lot of companies out there, not Hayward, but ozone companies who will remain nameless, UV companies who will remain nameless, that are making these claims already. And they're only using one type of technology. We went one step further, and we modeled the UV ozone system. This is work that primarily Professor Bolton did. And we took this kind of apparatus, and we looked at the mathematical modeling of it to see if we could predict what was happening. And there's lots of fancy math here. I won't bore you with it, but the bottom line is the science behind the absorption of UV light to generate ozone is well known. And if you look at the amount of oxygen in the air, the residence time, you can calculate the conversion and the amount of ozone that is made in an annular space around the lamp. And what he had to do is he had to break that annular space into little miniature hypothetical rings, and he calculated the generation of ozone within each of those individual annuli, and he summed them up across the length of the entire reactor to come up with the overall generation rate of ozone. It's quite complicated, but we ended up challenging that mathematical model with real data by taking 2 different lamps of 2 different intensities, and by passing air over those lamps at different flow rates, we were able to measure the amount of ozone that we were generating, and we compared it to the calculated value from the model. Okay? And on this slide, I'm showing you the comparison of the calculated versus the measured. The dotted line would be a perfect correlation between measured and predicted. And what you see here is our predictability or our predictive capabilities is quite good at low ozone concentrations, but things went to hell in a handbasket at the higher ozone concentrations, but we think we know why. So this is early work. What's happening at the high ozone concentrations, in order to achieve those, we had to slow the flow rate of the air down in order to increase the concentration. When we did that, the lamp temperature went up higher, and we're starting to destroy some of the ozone from thermal degradation, and we're also changing the efficiency of the UV lamp, because UV lamps, their efficiencies are very much dependent on their operating temperature. And so by slowing the flow rate of air down, we're not cooling the lamp as much, and the efficiency dropped. So there's really 3 reasons why our model is not perfect yet, and that is because we're probably seeing some thermal decomposition of the ozone at the higher temperatures. We've overestimated the efficiency of the 185 nanometer wavelength because the temperature is changing. And there, in fact, could be errors in the amount in the absorption coefficient for oxygen. So where do we see this going? I see this technology, particularly because the Model Aquatic Health Code is now in existence. I see innovation in this UV ozone space. I see both technologies growing. I see the combination of those technologies gaining lots of attention because, A, the Model Aquatic Health Code highly recommends that we go in this direction with one or more of those technologies. Number 2, we're going to continue to see outbreaks. I mean, unfortunately, hopefully they'll decrease, but nonetheless, they're still always going to exist. And you can get some great synergies with UV and ozone. So really, recreational water has been demanding this kind of solution, and I think this represents it. So I invite you to stop by for a demo, if you haven't done so already, and take a look at how we're combining UV and ozone and hydroxyl radicals to help take care of recreational water-borne illnesses. Thank you very much for your time and attention.
Thank you, Ray. I want to open up the questions. Yeah, I didn't think that would take very long. Please state your name, your company, and the question.
Brian Anderson, Water Design. You talk about low pressure UV. Does the synergy hold true for medium pressure, or does medium pressure not produce the 185 nanometers?
Medium pressure lamps do generate 185 nanometers. In fact, they generate an entire spectrum of different wavelengths. Those lamps operate at extraordinarily high temperatures, I think 1,000 degrees centigrade. So I'm not sure, I'm not aware, unless somebody else can tell me, I don't think anybody's generating ozone from a medium pressure lamp because the environment around that lamp is so hot. But low pressure lamps operate at, 150 Fahrenheit or so. Okay?
Hi, Rob Freely, Nationwide Aquatics. Your trial pool, the one you did the data on, could you describe the bather load you had in that pool to get that data?
Yeah, I don't have that with me, but this is a pool at our facility in Rhode Island, and the employees use the pool during the week and on the weekends. They don't anymore. They did during that particular. I would say I would not classify it as a commercial pool in terms of the bather load. I would say there was an average of 10 bathers during the weekday for the morning hours, the lunch hours, and after work. And on the weekends, there might have been 25, 30 people, including families and children. So not an overly excessive bather load whatsoever, okay, compared to what maybe you're used to, Ron.
I'm Michael Beatty from Disney Parks and Resorts. So if you have an existing UV on a body of water and you wanted to add the ozone, in your model here, it goes to the UV first. Did you try it the other way? Would it matter?
Yeah, you can do it the other way. Of course, you won't get the hydroxyl radicals generated, but you certainly will get the benefits of UV and ozone. And I would submit to you in that case, it's an additive effect, not a synergistic one, because you're going to have the impact of UV as the water goes through the device. Then you'll have the benefits of ozone after that. But you won't get the hydroxy-free radicals because you're not putting the ozone in front of the UV device, which is necessary for them to be created.
So that would be your suggestion? Is that
Absolutely.
Thank you.
Hi, Tom Schaefer, ETS. What's the effect on advanced oxidation, the free chlorine levels, or the chlorine consumption?
I have not personally studied that. There may be data in the scientific literature. I don't know, to be honest. You saw the data on the combined chlorines. I didn't look at free.
Steve Dunn, Commercial Pool Systems. I'm very familiar with the UV and ozone and combining the two together to get the free radicals.
Good.
I just want to say you did a very good job on the presentation.
Thank you very
and
much.
Explaining it to everybody.
Thank you.
More questions?